Hello everyone. Today we begin studying Chapter 5 of Signals and Systems, Frequency Domain Analysis of Systems. This chapter will reveal the rules governing a system's response to signals of different frequencies, which form the core foundation of communication system design and signal processing. Through frequency domain analysis, we can understand key issues such as how filters select specific frequencies and how systems cause signal distortion. Special note: Section 5.1, Frequency Response of Continuous Time Systems, is the cornerstone of this chapter. You must master both the physical meaning and the calculation methods of the system frequency response of h of j omega. The knowledge structure of this chapter is divided into 3 levels. The first is the theoretical foundation. From the frequency response of continuous time systems, Section 5.1, to the frequency domain analysis of discrete time systems, Section 5.2. The second is system characteristics. From the conditions for distortionless transmission, Section 5.3, to the principles of ideal filters, Section 5.4. The third is engineering applications. The time domain sampling theorem, Section 5.5. Hello everyone. Today we will study the zero-state response of a continuous time system to an arbitrary aperiodic signal. First, let us examine the zero-state response of the system to a complex exponential. We find that the zero-state response equals the product of the complex exponential and the spectrum of the impulse response, as shown in equation 1. Just now we understood the basic idea of the zero-state response. Now let us look at the detailed mathematical derivation, as shown in equations 2 and 3. From the above derivation, we know that the spectrum of the zero-state response equals the product of the spectrum of the excitation signal and the frequency response function, as shown in equation 4. The frequency response function has both magnitude frequency and phase frequency characteristics, reflecting the system's transmission characteristics for different frequency components of the input signal. The system frequency response h of j omega is the Fourier transform of the impulse response h of t. There are 3 methods for calculating h of j omega. Differential equation method. Take the Fourier transform of the system's differential equation. The differentiation property formula converts differentiation operations into algebraic multiplication. Impulse response method. Directly take the Fourier transform of h of t, the most fundamental method. Circuit model method. Establish a frequency domain equivalent circuit model, applicable to circuit systems. The choice of method depends on the given information. If the differential equation is known, use method 1 first. For example, in example 1, given a second-order constant coefficient differential equation, find the system's frequency response. We can use method 1 by taking the Fourier transform of both sides of the differential equation. Here, you should pay attention to the use of the differentiation property of the Fourier transform, which we studied in Chapter 4. Next, let us look at example 2. Here the unit impulse response h of t is given, so we can use method 2 to directly take the Fourier transform and obtain the frequency response function, as shown in the solution process in the figure. Next, let us look at example 3. In this case, the problem uses a typical RC circuit as an example. Input is the voltage source f of t. Output is the capacitor voltage y of t. We use method 3 to establish the frequency domain equivalent circuit model. First, establish the frequency domain model. The resistor R remains unchanged, and the impedance of the capacitor C depends on the signal frequency and the value of C. Second, according to the voltage division principle for series circuits, the ratio of the capacitive reactance to the total impedance is the frequency response function, as shown in the figure. after obtaining the frequency response function. Take the inverse Fourier transform to obtain the unit impulse response h of t. From the frequency response curve we can see, when the angular frequency is 0, the magnitude of the frequency response is 1, meaning the signal is not attenuated. When the angular frequency is infinite, the magnitude tends 0, meaning high frequencies are completely suppressed. Here we can see that this RC circuit exhibits a low-pass characteristic. As the frequency increases, the system's magnitude response decreases continuously. When the magnitude response drops to 0.707, the corresponding bandwidth is called the passband, also known as the system's 3 dB cutoff frequency. For the explanation of the above content, we will make a unified overview. Given a constant coefficient differential equation, regardless of the order n, we can take the Fourier transform of both sides of the equation and solve the resulting algebraic equation to obtain the frequency function of the zero-state response, as shown in the result. Next, let us look at an example to practice using the Fourier transform method to solve for the zero-state response, as shown in the problem. Given a second-order constant coefficient differential equation and a known input excitation, find the system's zero-state response. Seeing this problem, we first take the Fourier transform of both sides, then rearrange the algebraic equation to obtain the frequency response function, as shown in the result. From the known excitation signal, and using the fact that the system's frequency domain output equals the product of the Fourier transform of the excitation and the frequency response, we can obtain the system's frequency domain output. Then, by taking the inverse Fourier transform, we finally obtain the zero-state response as shown in the result. Alright, we have now completed section 5.1 of chapter 5. Let us make a brief summary together. Using the frequency domain method to solve for the zero-state response allows us to directly observe the change in the signal spectrum after passing through the system, to explain the differences between the time domain waveforms of the excitation and the response, and to clearly convey the physical concepts. This is the advantage of using the frequency domain method to solve for the zero-state response. What about the disadvantages? The frequency domain method can only be used to solve for the system's zero-state response. The zero-input response must still be solved using time domain methods. In addition, as we learned in chapter 4, a signal must satisfy the Dirichlet conditions to have a Fourier transform. This means that some signals do not satisfy the conditions for the Fourier transform and thus cannot be solved using the frequency domain method. Of course, for signals that do not satisfy the Dirichlet conditions, we can address this problem using the Laplace transform in chapter 6. Also, for some signals, the inverse Fourier transform is equally complex. These are the advantages and disadvantages of the frequency domain method.